Okay, so let's look at the problems. All right, so what we're going to do today is we're going to look at 4 problems. These are material, at least the first 3 are clearly from section 4.1 in the textbook. And the last one is sort of a strange problem that kind of crosses the boundary maybe between sections 4.1 and 4.2. It's a slightly different kind of problem, but it's a harder problem, but we'll get to that as the last thing we do today. All of these come from the problems at the end of the chapter. And so the main topic with 4.1, section 4.1, is that you are looking at algorithms that answer questions about different models of computation and language descriptions, right? So algorithms that work on DFAs, for example, or algorithms that work on context-free grammars, or algorithms that work on Turing machines. So questions you might ask about those. For example, given a particular DFA and a string, does the DFA accept the string? And these are all things that, that we have done in class. We've worked through ourselves. And I have stressed when we've done that you should be following the sort of mechanical procedures that are defined, for example, for converting a regular expression into an NFA, or converting a NFA into a DFA. And for all of those, we just had these procedures that if you have, so to convert an NFA to a DFA, you make states for all subsets of states of the NFA, and then connect those together based on the transition function. And then that creates a DFA. And you can just sort of mechanically follow those steps and do it, and you get a DFA. And the whole reason we were doing that by these mechanical conversion processes is because what we're really interested in is whether or not we can create algorithms, programs that do that same transformation. So could you write a program that turns an NFA into a DFA? Could you write a program that does that decay automaton construction, right? So that's where we were going with all of this. And at this point, so in chapter 3, we looked at details of the Turing machine model, and like in your homework on question 6, you write out at the level of the state transition diagram what the Turing machine looks like. In this chapter, we're really just concerned with algorithms, so high-level descriptions of algorithms. We're not going to draw state diagrams. We're not going to really even talk about what is on the Turing machine tape. You can think of this as basic pseudocode description of algorithms, and since algorithms are the same as Turing machines, we're really designing Turing machines. So there are a lot of examples of this in section 4.1, and one of the things you need to do is go through that and just be very familiar with and comfortable with the different languages that they have algorithms for in section 4.1. There is an algorithm given for, actually, let me Scroll through that real quick. So here is chapter 4 in the textbook, and the things that they talk about are all languages that are described in a format like this. For example, A sub DFA is the language of pairs B and W, where B is a DFA and W is a string, and the pairs that are actually in the language ADFA are pairs of DFAs that accept the string that's given in the pair. So you can think of this as a language. That's the language interpretation. You can also think of this as a yes-no question. You're trying to come up with an algorithm that when you're given a description of a DFA and you're given a string, you have to decide whether or not the DFA accepts the string. So that's this language. Theorem 4.1 here says this is decidable, and then this is the way it does it. It describes a Turing machine that always decides correctly whether a pair BW is in the language or not. So this is the format that we're going to use for several of our problems coming up. We're going to have a language. We need to show that it's decidable, so we give a Turing machine that looks like this. So this is one, asking whether a DFA accepts a string. The second one is asking whether an NFA accepts a string, right? So a non-deterministic finite automaton. Here is the same sort of thing, but for regular expressions. You're given a pair, a regular expression and a string, and you're asked whether that regular expression generates the string W. Okay, so everything was a pair of a machine or a regex and a string up to this point. eDFA is a little bit different because you only give it a description of a DFA, and you're asking, is the language accepted by the DFA empty, right? So does it not accept anything? Is an empty language. So that's another one that's decidable. EQDFA, you're given two DFAs and you're asked whether they accept the exact same language, right? So you can have a language that's accepted by very different looking DFAs, and this is just asking, are they equivalent? So those are a lot of things you can ask about DFAs that are all decidable. There's algorithms for all of those. There are algorithms on context-free grammars that are decidable. ACFG is you give it a grammar and a string, and you ask whether or not the grammar generates that string. So this is important. This is a general CFG. It's not the deterministic CFGs that we worked with, that we made parsers for in the current homework. This is arbitrary CFGs, but it's still decidable. The set of grammars that are empty is decidable. So every context-free language is decidable because it has a grammar, and then that was decidable. So the DFA questions were all done by the basic conversion algorithms that we had. One conversion algorithm that we never really used for anything, and you might have sort of wondered why we actually did that at one point, was, we did that conversion of CFGs to Chomsky normal form, right? The reason that we had that conversion process to create a grammar in Chomsky normal form is because it's used in this algorithm right here for determining whether a CFG generates a particular string. And to do that, the first step is you convert the grammar to Chomsky normal form. So you can tell whether it's empty, and so on. And so that's section 4.1. And like I said, the key point there when you review that section should be thinking about Making sure you're comfortable remembering everything that we've got algorithms for. And we're going to take those algorithms and build on them to create other algorithms. All right, that was a long intro to all of this. But now we're going to start on our problem. So exercise 4.2 here says, consider the problem of determining whether a DFA and regular expression are equivalent. Express this problem as a language and show that it is decidable. So we're asking whether two languages are equivalent. So what we're going to do is we're going to start to write the language out. And let me start by giving it a name. Actually, let me zoom in a little bit here. Let's start by giving it a name. And similar to the ones that we did, that we just saw, if you're asking whether two things are equivalent, we're going to name that EQ with the subscript. Now, EQ sub DFA was equivalence of two DFAs. Here we've got a DFA and a regular expression. So to avoid making that too outrageously long, I'm going to just call this EQRD for regular expression and DFA. Actually, let me put it in the same order as the problem says whether a DFA and a regular expression are equivalent, so we'll do it that way. Obviously, that doesn't make any difference. It's just nice for consistency. So we need to define this as a language, and so equals, it's going to look like this. And so what do you think this looks like? What do you think that the items of this language look like? All right, wake up. This is the interactive part. Yeah, good. So some of the ones we looked at previously had pairs of DFAs, for example, or a pair that was a DFA and a string. So what we're looking at here are pairs of a DFA and a regular expression. So what Emily has there in the chat is exactly right. So this should be DR such that let me clean that up. All right. So when we define this, yeah, so loosely we would say D is equivalent to R. What we really want to say is that the languages that correspond to D and R are the same, but we also need to say what D and R are. So for example, we will say D is a DFA, right? And R is a regular expression. Good. And how do we say that the two languages are the same? Good. So LD is the language recognized by the DFAD. And same idea, L of R is going to be the language that's recognized by the regular expression. And so that's the definition of the language that we're interested in. Okay, any questions about that? All right, so the form then that we complete this with is we need to define an algorithm or define a Turing machine that decides whether a pair dr is in this language or not. So following sort of the form, you can look back at the form and the proofs of the theorems that we just sort of scrolled through. We're going to say, let's define Turing machine M1 So we say, right, we're defining an algorithm. So we have an input, we have to say what the input is. And now we're going to describe the steps that it takes, right? So all of those started off exactly like this. It named the Turing machine. Here we're naming it M1. It said what the input is on input DR. And then there were a sequence of numbered steps, 1, 2, 3, 4, how many ever you need. So let me ask this. I said that you needed to be familiar with all of those things in 4.1 that it already gave algorithms for, right? There were 5, 6 algorithms in section 4.1. And we very seldom just do things from scratch. So we're going to fall back on one of those. What's the most relevant language to be thinking about using for this one? What's the closest to this? So that part is really central. We're testing whether two languages are equal. And when we're talking about regular languages and DFAs, there was one language that we had that did that, and that was the language of testing where two DFAs are equivalent, which is what Fernando said in the chat. So the name of that one was EQ sub DFA, and so that's where we're headed with this. That was the only one that compared two entire languages. So we're going to try to use that when we construct M1. But we don't have two DFAs to compare, right? We have a DFA and a regular expression. So how do we solve that problem? Good, right. So convert the regular expression to a DFA, or as Fernando said, convert it to an NFA and then to a DFA. The end result is that we're converting the regular expression into a DFA, and then we're going to check to see whether the language accepted by our new DFA is the same as the language that's accepted by D that's given as part of the input, and then that'll tell you whether D is equivalent to the regular expression. So, whether you do that in one step or two is sort of up to you, depending on how much detail you want to use. I would probably look back into chapter 1 and see if there's a result that does it directly from a regex to a DFA, or if we went through separately. But let me put them both in one step of this algorithm. I'll mention both parts, and then talk a little bit about how you document this. So the first step is we convert So we're going to call that DFA-B. So if you're writing this up and it's a written assignment problem or something that you're writing to show to somebody else for documentation of something, you really should refer to something specific as to how you do this conversion, right? So I think everybody remembers doing this because you did it on homeworks, you did it on the first exam. So converting a regular expression into an NFA is something we've looked at a lot, and an NFA to a DFA is something we've looked at a lot. But just from a documentation standpoint, it should refer specifically to, theorem 1 point something, something, something. And I would have to look back in the textbook to pull that up. In an exam setting, I wouldn't expect you to document it at that level. I did tell you earlier that this exam is going to be open book. The less you can refer to the book, the better. You should know these things, and with the thought in mind that you should know these things, you don't have to cite a specific theorem because nobody should have to remember what theorem 1.28 does, for example. I don't know if that's a theorem. You could, if you want to be a little bit more precise than what we've got here, you could just say chapter 1 rather than citing a very specific theorem. That would be fine. But the point is that if you have the time to document things fully, cite something specific. Stephen says that the conversion to an NFA is theorem 1.54. So you could cite that, and then the NFA to DFA conversion as well. But we're going to leave it like this for here, just knowing that we could go back and fill in that detail if we needed it, right? Okay. So now we have a DFA-B, and it's equivalent to our regular expression R. So now, let me go ahead, since I did have I'm not going to share this screen back, but I'm going to look in the textbook. I have it here. Theorem 4.5 tests whether or not the languages accepted by two DFAs are equivalent. So, and inside the proof for theorem 4.5, just like we've got a definition of a Turing machine M1 here that we're doing as part of this proof, in that the name of the Turing machine that they created was F. They created a Turing machine F. So we can say use So I'm going to write out the second step like this. I am writing a little bit more detail here, an explanation of why we're doing this than the textbook does in their descriptions. So in other words, they might have just said, use Turing machine F from the proof of theorem 4.5 to decide if DB is in EQ sub DFA without explaining why. But I'm going to add this little note here that, in other words, we're deciding whether or not the language recognized by D, our original DFA, is equal to the language recognized by B, this DFA that we just created, with a little note there that that's equal to the language generated by regular expression R. And then as the last step, we just say and you'll see if you go back through section 5.1 that a lot of their algorithms, their proofs, end up turning this into a problem on a different language where the answer is exactly the same, right? So here, the answer to our question of whether D and R are equivalent is the same as whether D and B are equivalent. So if F accepts, we accept. If F rejects, we reject. And that is the entire answer. So you can go back and you can compare that to the proofs of other things in section 4.1, and it will be, you'll see that it's pretty similar, and that the style of these is the structure and the style is all the same for all of these different problems. So any questions about that? Okay, so to kind of recap the way you approach a problem like this, we look at what we're trying to create an algorithm for. We think about whether or not it's equivalent to or similar to something that we already know how to decide. And then we write an algorithm that takes the input to this problem, converts into something we can use for a known problem, and then use the algorithm to decide that problem. And that's the way all these things are working in section 4.1. All right, we'll go on to the next one. So exercise 4.3 is about a language all. It's called all sub DFA. And it's the language of all DFAs where the language recognized by the DFA is all strings over the alphabet, right? So in other words, all strings over the alphabet sigma is just sigma star. And so we're asking whether the language of DFA A is equal to sigma star, whether the DFA accepts every possible input string. So I copied this out of the book as exercise 4.3. It actually would be slightly more interesting if this were all sub NFA, but all sub DFA, I mean, if you think about what you would do looking at a picture of a DFA, you just need to make sure that every reachable state is a final state, is an accepting state. Now, you could say that pretty easily as far as what you would look for if you were examining the state diagram, but turning that into an algorithm that we can use here is a little bit more complicated. I said every reachable state. We haven't done anything where we talk about looking at reachability of states or anything like that. So let's try to stick with just the things that are already proved in section 4.1. So accepting a string in a DFA or an NFA, generating a string with a regular expression, testing whether or not a language is empty, or testing the equivalence of two DFAs. So I can think right off of two pretty straightforward ways to do this. And so what I'm going to do is I'm going to let you guys kind of guide how we do this. So let's start off the description the same way we did the other. Right, all of these work. We're going to define a machine M2 that we already know what the input looks like, right? So the language definition is given to us here. We don't have to write it out. So on input A, where A is a DFA, so that's how we start. We say we name the machine, we say what the input is, and now we have to figure out what we're doing. Like I said, there's several different ways to do this. I'm not stuck on any particular algorithm, so I'll let whoever wants to throw out suggestions sort of guide how we go on this. What existing language that we have an algorithm for, what existing problem on DFAs do you want to use for this? Okay, somebody give me an idea. Everybody awake out there? Raise your hand if you're awake, or click yes or something. Okay, so we have some people that are awake. But I'm guessing that.
Excuse me.
Yeah.
Okay. I don't know where to begin, but would it take us anywhere if we proved that the DFA recognizes the the alphabet? I don't know where we should continue this definition from. Should we prove that the DFA recognizes all the alphabet? Should we prove that? Should we write a Turing machine to recognize the alphabet?
So you're given the DFA, and so your part of the DFA's description is the alphabet, and you're given a transition function, which is given as like a table of values. You know, if you have this input symbol from the alphabet and you're in this state, then you go to this next state, right? So that's what A is. A is a complete description. You can think of that 5-tuple we had of the DFA. So you know the alphabet, and you know the transition function, and you know all the states. And so that's what you have as input to process. So you don't have to determine whether the DFA works on the alphabet or whatever. Because by definition, you're given a DFA and you're given the alphabet, and you're given the transition function in terms of the alphabet. So it's always going to process that. Let's go through. I'm going to make a little note out here to the side. Some of the languages that we have. So A sub DFA. A sub DFA is the first one they look at in the section. And it's a language of DFAs and strings. It's like A comma W, and it's asking whether A accepts W. So it's a question about not the entire language that DFA recognizes, but it's a question about a language and a specific string. So is this a question about one specific string? Is all DFA is about one specific string, or is it about a language as a whole? Right. So It's about the language as a whole. It's asking whether every single string over the alphabet is in the language, right? In other words, the DFA accepts everything. I don't care what you give it, it accepts everything. So a sub DFA deals with a specific string, so that's not it. A sub NFA is the same, so let's just sort of skip over that one. What did we have? We had A sub regex, something like that, that was about a string and a regular expression. The first one that we had that seems like it dealt with a language as a whole is E sub DFA. E sub DFA asks whether the language accepted by an input DFA is empty. In other words, whether the DFA rejects everything. So is that a question about a language as a whole or one string in the language? Good. So now we have a known language with a known algorithm, E sub DFA, that can tell whether a DFA rejects every string over the alphabet, right? And in fact, if you think about that for a second, that sounds a little bit like what we're asking about here. So all sub DFA is asking whether the DFA accepts every possible input string. E sub DFA, whether the language accepted by the DFA is empty, is asking whether the DFA rejects every string over the alphabet, right? So those are pretty similar. Let me go ahead and just for completeness here, we'll put in the last language, and that's what we used in the last problem. EQ DFA was a question about two different DFAs. And again, it's a question about a language as a whole, right? So you have an A and a B, and you're asking whether the language accepted by A is equal to the language accepted by B. It's not about an individual string, it's about the language as a whole. So both of these are about languages and about DFAs that recognize, that accept languages. And so we're going to focus on those as our best candidates for using for this problem. With that description, does anybody have any ideas now of which one of these two would be easy to use? Stephen. Stephen, you've got a hand raised. Are you giving an answer, or is that just left up there from earlier? Left over. Okay. Well, Rashmi and Lavanya in the chat said E sub DFA. So this language of whether or not a DFA, the language recognized by a DFA is empty. So we're going to try to use that. So if we're going to use that, we need to create a machine, a DFA, that we can ask, is the language accepted by this DFA empty? So what we can do is we can use any of the conversion procedures to turn A into a different DFA that then we can ask whether or not the language recognized by our new DFA is empty. So any ideas for this? Good. So one slight correction to what Fernando said. Fernando says, can we get the complement of A? So A is actually a DFA. It's a machine. So machines don't have complements. Languages are sets, and languages have complements because sets have complements. So we don't talk about getting the complement of A, but we can talk about getting the complement of the language recognized by A. So the complement of L of A. So that's the right idea. Just be precise when you write it down to use the right set notation, set terminology. Now, if we have a DFA that recognizes L of A, how can we turn that into a DFA that recognizes the complement of L of A? Good. So we swap accept and reject states. Now, again, a little bit of terminology. We didn't have reject states in DFAs. We did have acceptance states, or we had final states. So what we want to do is turn everything that's a final state into a non-final state, and everything that was a non-final state into a final state, right? So I like your word swapping better. So we created DFA B by taking A and swapping final and non-final states. When we do that, the language accepted by B is the complement of the language that was accepted by A, right? So everything that was accepted by A is not accepted by B. Everything that was not accepted by A is accepted by B. So that means that the language recognized by B is the complement of the language recognized by A. All right. I'm going to make another note. The other sort of explanatory note that we can put in here is that since L, the language recognized by B is the complement of the language recognized by A, that L of B is empty if and only if the language recognized by A is the set of all strings, right? So L of B is empty if and only if L of A is everything. So now what we've done is we've changed this into a question we can ask about language B. And we go back to the textbook and we see that the Turing machine that decided E sub DFA is in theorem 4.4 and the name of it is T. So and then there's our definition, right? Since the language accepted by B is empty if and only if the language accepted by A is everything, is all strings, then If T says that L of B is empty, then we accept because L of A is the set of all strings and reject otherwise. And that's the whole definition then, right? And again, the book tends to write explanations outside of the definition of the Turing machine, of the language. And you'll see that I put little notes in here, kind of like comments in the code, I guess you could think about it, that explain why this works. And if those comments are complete enough, then you don't really have to explain outside of this why this Turing machine works. I think from the note that L of B is empty if and only if L of A is the set of all strings, it's clear why this machine M2 decides the language all sub DFA. All right, any questions about this? This seems to have stumped people at the beginning. Is there anything unclear that you would like to go back over with this? All right. Let me just add a note real quick. I said at the beginning that there were two main ways that you could do this. And this was one of them. Right. So Brandon says in the chat, I think it's a lot to do with how to reference the book's problems. So just make sure you know the names, right? So there are 5 different languages that are given in the book that deal with regular languages and finite automata. There's A sub DFA, A sub NFA, A sub regular expression, whatever that one was. Then there's E sub DFA for empty languages and EQ sub DFA for equivalents of 2 different DFAs. If you know those and you remember all the conversions we could do from chapter 1, you know, NFA to DFA, regular expression to NFA, then it's just a matter of putting the puzzle pieces together in the right order. But you have to be comfortable enough with all of the things that are defined in section 4.1 so that you know how to put the pieces together. Let me say real quick that the other solution to this that I had in mind actually used the EQ DFA language instead of the empty DFA language. So EQ DFA tests whether 2 DFAs accept the same, or whether they recognize the same language, right? And so all sub DFA is asking whether DFA accepts every string in the language. So another thing we could do is we could just define a DFA-B that accepts every string in the language, that we know accepts every string in the language, and then see if that's equivalent to A, right? So and this is a simple DFA, one state, and the transition function has that one state always going back to itself no matter what symbol from the alphabet is seen. And then this accepts every possible input, right? So we can easily create a DFA that accepts every possible input and then ask whether or not A and B recognize the same language, right? And then this also solves the problem. So the main thing was asking a question about a language, right? About, so either E sub DFA or EQ sub DFA rather than specific strings, and then figure out how you can rewrite the problem to use that. And so either one of these would work just fine. Any questions about that? All right. So here's one that uses some set notation. And we're asking whether the set of strings generated by regular expression R is a subset of the set of strings generated by regular expression S. All right. So this one is a little bit more complicated. I will say that most of the decidable languages, when you're talking about regular languages, most of the algorithms that we have in regular languages deal with DFAs. They don't deal with NFAs, they don't deal with regular expressions, but we can always convert a regular expression to an NFA and then an NFA to a DFA. So we can always take everything that we're given, no matter how you describe a regular language, whether it's a regular expression, NFA, or a DFA, and convert it to a DFA and then work with a DFA. So that's the first thing you ought to think about with these. How do I state this in terms, let's not get sidetracked by the fact that the question's asking about regular expressions. You should be thinking in terms of DFAs. And when you're thinking in terms of DFAs, let's think about, we're just going to make some notes here. We're asking whether one language is a subset of another language. What this really is, we're saying that every string in L of R is also in L of S. That's just what a subset means, right? So one of the things that you definitely should do is go back and study the construction that they did in the book for the EQ DFA language, determining whether two DFAs accept the same language. And what they did is they turned that into operations on sets. And, we can do complements, we can do unions, we can do intersections, and all of these were DFA modification algorithms that we talked about in chapter 1, right? Do you remember how, we had, at one point we had two DFAs, and we created a new DFA that recognized the intersection of the two languages of those two DFAs, right? And then we did another one where it was the union. And both of those constructions did that by starting off creating a new DFA where the set of states was the cross product of the set of states in the two input DFAs. So that's the kind of thing that we do here. And so what we're going to do is see if we can say something in set notation and ask whether a certain set is empty, or maybe it's the set of all strings, since we just did that. Where the set formula is empty if and only if something interesting that we're trying to solve is. So can you come up with, let me take one more let me sort of flip the sense of this around. Okay, so this is how you can reason about this with sets. So L of R is a subset of L of S if and only if every string in L of R is also in L of S. And so it's easier to think about when our condition is violated, when L of R is not a subset of L of S. And so it's bad if there is some string X that's in L of R, but it's not in L of S. And now we're saying that this is bad if X is in L of R and in the complement of L of S. So can you think of how we say that with just set operations instead of writing out sentences? So how do I determine if there's an X that's in L of R and also in the complement of L of S? Intersection, right. So we're looking for something that is in both L of R and the complement of L of S. And so that's what we're really asking. Is there a string X in L of R intersect the complement of L of S? All right. Asking if there's a string in a set is basically asking if the set is non-empty. And you know what? We have an algorithm to determine if a language is non-empty. So actually, let me call this so we're going to convert R into an equivalent DFA. We're going to call that A sub R. It's the DFA that is equivalent to R. It recognizes the same language as R. Okay, so now we convert S. Remember, it's a regular expression. We turn that into a DFA-B. Then we swap the final and non-final states to basically complement the language that it recognizes. We're going to call that DFA A sub S bar, where the language recognized by A sub S bar is the complement of the language generated by regular expression S. Then So now we create a DFA for the intersection of the DFAs that we created in steps 1 and 2. And then the result of that, because of the set operations that we pointed out above, the result of T, right, it tells us whether that's empty. So basically T is looking for counterexamples to L of R being a subset of L of S. And if no counterexamples exist, if that is the set of counterexamples is empty, that means that L of R actually is a subset of L of S. So this is definitely more complex than the previous ones we did. It would have been a little bit simpler to start with the DFAs, and then we don't have to get confused with regular expressions. But that's always the first step with any of these. If you're given regular expressions, convert them to DFAs. If you're given NFAs, convert them to DFAs. And then think about how set operations can get you to where you need to go with one of the known decidable languages like E sub DFA. So like I said, that one was more complicated. Any questions about that? Let's see, so let's see. So Stephen's comment was, could you convert RNS to DFAs and then create a new DFA that recognizes the intersection of those? Now, so yeah, so then the L of C then, as the intersection, would be exactly L of R if and only if R is a subset of S, right? And then you could use EQDFA on R, and on R converted to a DFA directly and C, yes. So that you could do, and yes, that would work. So that's another good way to do this. Brandon's comment, so just make sure. Yeah, so Brandon, your initial comment there, that's exactly right. So if L of A sub R had something that was outside of the set, if we had actually created a L of A sub S instead of an L of A sub S bar, then anything outside of L of A of S and inside L of A sub R would make this intersection that we did non-empty, right? So again, that's a counterexample. It's something that's in the language generated by R, but not in the language generated by S. And so that counterexample means that our intersection set would be non-empty, and that's why this works. All right, other questions? Okay, so the last one I had here that we're not going to do is it's a relationship between um, Turing machines for things that are decidable versus things that are recognizable. It's not about DFAs or it's not about CFGs or anything like that. So it is a little different from the other things in section 4.1. The fact that we didn't get to it is not a huge deal because it's really not central to this. It's a really important question for later on in the course. Really, this will come up and be vital in chapter 5. It's okay if we skip this until chapter 5, but I'll give you a little challenge to think about this. Give priority to getting your homework done and that sort of thing. But if you have time to think about this, it's a good challenge problem, and it is important for something that we do in the future. Okay. So with that, we'll close this problem session. If you have questions about the homework that's due on Wednesday, send me an email. I'll do my virtual office hours on Wednesday as usual. One thing I would strongly suggest that everybody do based on what happened in the office hours today, sometime just like on your own, use Zoom and test your setup, right? So make sure you can make your microphone work and that sort of thing. So make sure that you have everything unmuted and know how to get that to work, because it's frustrating in office hours if you come in and you make the connection and then I can't hear a word you say, and the chat window really is just not high throughput enough to discuss these problems. So there we are. Any last minute questions before we call it quits for today? All right. Well, everybody have a good next couple of days, and we'll talk to you on Wednesday.